In this video, we'll look at how we can train a neural network and then test the accuracy of our predictions. So we mentioned before that due to the size of the data sets that we typically use for deep learning models, we have to iteratively improve. We have to iteratively improve them by training on one batch of input data at a time, rather than trying to train on the entire data set as we've done in the past. One analogy for this is it's kind of like cooking a meal, but instead of just adding the entire amount of salt that you're supposed to add according to some recipe, you instead add one little grain of salt, and you give it a taste test. And if you decide it's not enough salt, you add another grain of salt, you add another taste test, right, and so on. And you just add the salt one grain at a time, right? Um, uh, so you can still get to the right amount of salt, right? But you have to do it piece by piece. So how does that look like for deep learning models? Well, the first thing we do is we load a batch of images. We use those data loaders that we've already learned about. Then we make what's called a forward pass over that batch of images, right? So we make a prediction for each one of the 32 images. In our case, for the MNIST dataset, we predict which of the 10 digits is in each of those 32 images. And then, since this is the training data, right, we can compare our prediction to the actual digit that is in each of those images. Then we slightly improve each node's coefficients, right? Remember that each node was effectively a linear model, right? So we slightly improve the slopes and intercepts of each of those linear models, right? So that the model is slightly more accurate at making predictions for those 32 images. Okay. And then we repeat, right? And once we've gone over the entire data set of images, right? Remember we had split out 50,000 of the images into our training data, right? We'll go over those 32 images at a time. And once we've been over all 50,000 images, that is called an epoch of training. Typically, we run deep learning models for many epochs, right? So once we've gone over all 50,000 images, then we go back to the start and we repeat the process, right? Because what we may have found is, to go back to our cooking analogy, we have not yet added enough salt to the pot, right? So we go back over the images again and we keep on improving the model's coefficients. So to set this up with the torch package, we're actually going to use a function from the loose package, which makes this easier for us to write. Okay. The first thing we're doing is we're piping in the net variable that holds the architecture of the model we previously defined. Then the loss argument we use to specify how we calculate the model's inaccuracy, its error, how wrong it is with its predictions. We're using this function here, which uses something called cross entropy as a way of calculating the inaccuracy. Then we need to also supply an algorithm that is used to improve the coefficients each time. Okay, here we're using something called the Adams optimizer. And then here we have an optional argument where we can indicate any other metrics that we wish to calculate, right? So we'll automatically get the cross entropy loss calculated for us, since that's the way that we're calculating loss. But if we want to calculate any other metrics, right, then we can supply them here. So here we're also going to just calculate the accuracy, right, the fraction of predictions that we get correct. Then we can use a function called the fit function, which is also from the loose package. Okay, so now we're piping the model variable that we created on the previous slide. We pipe it to fit. We specify the data loader for the training data, okay, the number of epochs that we want to run the model for. Right, remember, that's the number of times that we pass over the entire data set. Here we're also supplying the validation data with the validation data loader. Okay. And we're using this verbose equals true argument so that we get more output reported by this function. Once this is completed, and it might take a while to run the fit function, okay, then the output we'd stored in a variable called fitted, and we can use the plot function to create a ggplot graph showing how the model's loss and accuracy change throughout the training process, right? So each one of these points in these graphs represents the values of these metrics at the end of a particular epoch, right? Remember that we trained for 10 epochs. Right, so we've got 10 points here, and we can see in this top row, right, we have the accuracy. The accuracy improves over time, right? As we train the model more and more, they get more and more accurate. Unsurprisingly, right, the training graphs look pretty good, right? The more we train on the training data, the better we get at making predictions on the training data. The validation data is not quite as accurate, unsurprisingly, right? Because we're not using this data to create the model. So inevitably, it's going to be slightly worse at making predictions on this validation data. Looking at these curves after you train a deep learning model is very important because deep learning models are so complex that they can run into a problem called overfitting, where if you train the model for too long, for too many epochs, then the model can get too good at predicting the values in the training data set, right? Which will mean that it can then get worse at making predictions on images that weren't in the training data set, okay? So typically, when we're training these models, we have to manually set the number of epochs that we want to train for, okay? And so we have to figure out at what point do we stop. So we want to stop ideally before we get to the point of overfitting, okay? One way we would know that is if the training loss, right, that we see here in this bottom left graph keeps on improving. So we keep on getting better and better and better at predicting the numbers in the training data set, and that never stops improving, then that can be a sign of overfitting. Another sign is that the validation loss, which we see here in the bottom right, stops improving, right? Here you can see it's kind of plateauing. Here it even looks like it's actually getting worse again, right, in the second from last point. And that can be a sign, another sign that we have reached the point of overfitting, right? We're not getting any better at making predictions on data we haven't seen before. Another sign of overfitting is that we have a big gap between our loss on the validation data here and the training data here, right? Obviously, we're going to expect some difference, but we don't want it to be too big. Ideally, we want them to we want to stop training before they start to significantly diverge. So how can we make deep learning models more accurate, right? Well, if the model is underfit, right? So by that we mean that we can still improve it. Then one solution is just to run for more epochs, right? So you keep on improving the coefficients of the model. Another way is to make the model more complex, right? You can add in more hidden layers or more nodes into those hidden layers. If you have overfit, right, then typically one thing you'll definitely want to do is stop training earlier. Okay, so you'd identify the point where the model starts to overfit to the data, and you then retrain it, but stop at that many epochs. You could also simplify the model, right? Reduce some of the nodes or take out some of the hidden layers, or you can add more data. The other thing you can do, and we're not going to discuss this much here, is something called regularization, which is a method of penalizing parts of the model that aren't contributing too much useful information to the predictions and taking those out of the equation, which is kind of like simplifying your model as part of the training process rather than having to define a simpler model before doing the training. So typically the way this works, right, if you're doing this in practice, is that after you've trained the model, then you adjust it, you retrain, you recalculate the metrics on the validation set until you're satisfied with the validation accuracy. And then you take that best model that you've created, and the final step is to then calculate the generalization error on the test data. Okay. So we have another set of images that we haven't even looked at yet, right? The test images, and these represent a way of measuring how well the model will do on data that's truly never seen before, right? Because even though we've held back the validation data from the training data, the fact that we're using the validation data to pick our best model means that we're going to slightly be biased towards being more accurate on the validation data than we would otherwise be, right? So the test data represents data that hopefully the model is not biased towards being more accurate on than it should be. Okay, so we have to do the same steps before to prepare the data, right? We're using the MNIST data set. Here we specify the additional argument train equals false so that we get the test data. Then we create a data loader, okay, using the data loader function. And then finally, we can use the evaluate function. We supply the model, the fitted model as the first argument, and the test data loader as the second argument. And it calculates the loss and the accuracy of the model on that data.